Assalamualaikum and good day to our lecturer, Dr. Zul Adlan. We are from Group AS1205D and this is our video presentation for subject CHM361. Our topic is about metallic bonding and band theory, and the main title is about understanding the science behind metal. So let us begin. And for our team, my name is Humaira Adlina, and the rest Siti Maitatun Nadira, Nurin Nadira, and we have Nur Shafika and also Nur Nabilah Izzati. The objective of our video presentation is to explain metallic bonding, to describe the state of electron model, to relate metallic bonding to properties of metal, to introduce band theory, to differentiate conductor, semiconductor and also insulator, and lastly to connect band theory with real-life application. Introduction. In our daily life, we use many metal objects such as electrical wire, cooking utensil and electronic device. One important property of metal is that they can conduct electricity and heat very well. However, not all material can conduct electricity. For example, metal can conduct electricity easily. Semiconductor conduct electricity under certain conditions, while insulator cannot conduct electricity at all. And to understand why these differences occur, we need to study metallic bonding and band theory. These two concepts help explain the behavior of electron in metal and other material, as well as their physical and electrical properties. What is metallic bonding? Metallic bonding is a type of chemical bonding that occurs in metal. In metallic bonding, metal atoms lose their valence electron and form positive metal ion. These positive ions are arranged in a regular lattice structure. The valence electrons that are released do not belong to any specific atom. Instead, they become delocalized electrons and move freely throughout the entire metal. The metallic bond is formed due to the electrostatic attraction between positive metal ion and the sea of delocalized electron.
This diagram shows the sea of electrons model in metallic bonding. In a metal, atoms release their valence electrons which become delocalized. The metal atoms then form positive metal ions that are arranged closely in a regular lattice. The delocalized electrons are not attached to any one atom. Instead, they move freely throughout the entire metal structure, forming what is called a sea of electrons. The strong electrostatic attraction between the positive metal ion and the negatively charged electron holds the metal together. This model helps explain why metals are able to conduct electricity and heat. This slide explains the properties of metal from metallic bonding. First, luster. Metals are shiny because the free electrons on the surface reflect light. This property is commonly used in jewelry such as gold coins. Next, heat conductive. Metals are good conductors of heat because delocalized electrons can move freely and transfer heat energy throughout the metal. This allows heat to be transferred to safer surface such as clothes. Next, ductile. Metal can be stretched into wires. This is because metallic bonds are flexible and can break and reform when the metal is pulled. Moving on to malleable. Metals can be compressed into thin sheets. The layers of metal ions are able to slide over each other without breaking the metallic bonds, which is why metals are used in road sign. Next, strong. Metals are strong because metallic bonds do not break easily and can reform. This allows metal to absorb force, for example when hit by a hammer. Finally, electrically conductive. Metals conduct electricity because the delocalized electrons move freely through the metals and carry electric charge. This is why metals such as tungsten are used in light bulbs to produce bright white light.
Assalamualaikum, and my name is Nur Nadira. I'm going to present energy levels in solid, intro to band theory. So now I will explain energy levels in a solid using basic band theory. So what is band theory? Band theory is how delocalized electrons move through energy bands that are formed when many atomic orbitals overlap in a solid. This model helps to explain why metals can conduct electricity so well. Next is band gap and conduction. What is band gap and conduction? The energy difference between the valence band and the conduction band is called the band gap. Current flows when electrons gain enough energy to jump across this band gap from the valence band into the conduction band, which is like moving from the highest occupied molecular orbital to the lowest unoccupied molecular orbital. The size of this energy requirement controls how well a substance can conduct electricity. Next slide is the difference between valence band and conduction band. Valence band has filled or partially filled with valence electron, while conduction band has empty or partially empty band. Valence band has lower energy molecular orbitals where electrons bound to atoms, while conduction band has higher energy molecular orbitals where electrons free to move. Valence band has source of electrons for conduction, while conduction band carries electric current.
A conductor is a material that allows electricity to flow very easily. Based on the band theory, conductors such as metal have their own valence band and conduction band overlapping. Because there is no band gap, the electron can move freely without needing additional energy. This is why metals like copper and aluminum are highly conductive and are commonly used in electric wiring. For example, inside electronics devices like smartphones. Semiconductors have a small band gap. This means their electrons only need a small amount of energy, such as heat or light, to jump from a valence band to a conduction band. When more electrons can jump, the material becomes more conductive. Semiconductors like silicon are used in devices such as smartphones, where microchips control the flow of electricity to process information.
Next, I will explain about insulator. Insulator are materials that do not conduct electricity because their electron cannot move freely. In insulator, the valence band is completely filled with electron, while the conduction band is empty. There is a large band gap between the valence band and the conduction band. Because of this large band gap, electron cannot gain enough energy to jump into the conduction band. As a result, electric current cannot flow through insulators. For example of insulator, which is include rubber, plastic, glass and ceramic. Insulators are very useful in daily life because they prevent electric shock, protect electrical components, and are commonly used as safety material in electrical systems, such as the coating of the electrical wires. Next, I will discuss the real-life application of band theory. First are metal, which acts as conductor. Metals are used in electrical wiring and power cable. This is because their valence band and conduction band overlap to allowing electrons to move freely. Therefore, metals have high electrical conductivity. Common examples of conductors are copper wire and aluminium cable. Next are semiconductors. Semiconductors are widely used in transistor, microchip, smartphone, and solar cell. They have a small band gap, which means electron can move to the conduction band with a small amount of energy, such as heat or light. Because of this, the electrical conductivity of semiconductors can be controlled. Examples of semiconductors include silicon and germanium. And lastly are insulators. Insulators are used in cable coating, circuit board insulation, and electrical safety equipment. This is because insulators have a large band gap which prevent electrons from moving easily. As a result, they prevent current leakage and improve electrical safety. Examples of insulator include plastic, rubber, and glass.
In conclusion, metallic bonding explains how the localized electron allow metal to conduct electricity and display unique physical properties. Band theory further helps us understand how energy band and band gaps determine whether a material acts as conductor, semiconductor, or insulator. These concepts are fundamental in chemistry and play an important role in modern technological application. That's all from us. Thank you for watching.